Course 3, Investigation 3, we are looking at our quadrilaterals in a ton of different ways in this investigation. We're also looking at the golden ratio, or the Fibonacci numbers and sequence, and working with symmetry when we look at the quadrilaterals. So the first thing that we're going to look at with each of these is being able to say, well, what type of quadrilateral is it? How many parallel sides does it have? Things like that. So recall that a four-sided polygon is called a quadrilateral. Refer to the quadrilaterals shown below to answer the problems that follow. So we have A through G here, all different types of quadrilaterals, and the first thing we're going to look at is parallel sides. Well, remember that parallel sides means that we have sides that are equally far apart forever and ever and ever. For example, with letter A, if I were to look at this side and this side, those are the same distance away, and if I were to continue these lines forever in all directions, they would never ever intersect. So we would consider those parallel. So A has one set, okay, that side and that side, but it also has a second set here and here. Those are also parallel. So we definitely know that figure A has two pairs of parallel sides. Figure B also has two pairs, one pair right here, one pair with these slightly slanted sides, so B also. C, just like A, is a square or a rectangle like A, and it has two pairs as well, just like A. And D is very similar to B with those slanted sides. Now once we get past those ones, E, we have definitely two that are parallel here, so one pair, but these next ones, if I were to continue them, they would actually cross. So we would say, you know what, E only has one pair. So it's actually number 2 for E, just has one pair of parallel sides. F, unfortunately, these two sides are not actually parallel because they will intersect. So F is not going to work in either of these. Nope, those are not parallel. And G also doesn't have any pairs of parallel sides. So we would say for number 3, F and G don't have any pairs of parallel sides. So from this, we can actually name them pretty well. So one way to classify quadrilaterals is by the number of pairs of parallel sides. Quadrilateral with two pairs, here's a vocab term, is called a parallelogram. So here we have 4 parallelograms. Notice that the sides are all parallel. So which of the figures had those two pairs of parallel sides and therefore is a parallelogram? Well, we figured out that A, B, C, and D are all actually parallelograms. Now, which ones are trapezoids? Well, that's quadrilaterals with just one pair of parallel sides. The figures shown below are trapezoids. Identify each pair of parallel sides. Notice that the parallel sides of a trapezoid are not the same length. Well, in our original figures A through G, which ones did we find has just one pair of parallel sides? Well, we said that E just has one pair of parallel sides. That's all we have. So E is actually a trapezoid. Now we can actually name different types of trapezoids. For example, if the non-parallel sides of a trapezoid are equal in length, then the trapezoid is called an isosceles trapezoid. So for example, this one below has pairs of parallel sides, all right? There's our parallel sides. And then they're saying if these non-parallel sides are equal in length, that's what those little hash marks mean on the sides there, then it's called an isosceles trapezoid. Just a different type. All right, and then lastly, we have a couple more vocab terms. A quadrilateral with no pairs of parallel sides is called a trapezium. And we show 2 examples. The figure on the right is called a kite because a kite has 2 pairs of adjacent sides that are equal length, and I'll discuss that in just a second. So which of the figures are trapeziums? Well, our trapeziums are F and G, because those are the ones that had no pairs of parallel sides. And then which one is considered a kite? Well, G is considered a kite, because when we go back up here, definitely doesn't have any pairs of parallel sides, this G, but what it's saying is the adjacent sides, so this one and this one, are the same length. And then these 2 adjacent sides are the same length. We use hash marks to show things that are the same length. If they have the same amount of hash marks, so 1 and 1, then those are the same. 2 and 2 are the same. So that is considered a kite. G is a kite. No pairs of parallel sides, and those adjacent sides are the same length. So we can sort these into different types of quadrilaterals as shown in this box right here. So number 7, we can further classify some types of parallelograms. So we're looking at our parallelograms A, B, C, and D. Which of the figures A through G have 4 right angles? Well, 4 right angles, those are our boxes. So our rectangle A and our square C have 4 of those 90-degree angles. So A and C have those 4 right angles. So what we call this is, of course, a rectangle, the name that we've been using for many years now, hopefully. And so then we can continue to classify which of the figures have 4 sides with equal length. Well, equal length, they're all the same, and we can make some assumptions here, so I'll erase some of these lines so you can see them better. But in A through D, which ones have the same length of sides? Well, this one looks the same as this one. It would have to be since it's a rectangle. And these two look the same, but they're not all the same. So we can't consider A as ones that have all the sides being the same. My square does, though. These are all the same, so C does. And then D actually does. We have to make some assumptions here, but yes, D actually has all of the same lengths of sides. So we can name this, C and D are what we figured out. We can name this a rhombus, 4 equal length sides in a parallelogram. So specifically it's parallelogram, and then if it has all 4 sides being the same, we would consider that a rhombus. So which figure in A through G is both a rectangle and a rhombus? So which one has both 4 right angles and 4 sides of equal length? Well, C is the same. So we would say that it's both a rectangle and a rhombus. That is C. Our squares, all squares are both rectangles and rhombuses. So we can show all of this information in a Venn diagram, okay, and figure out a lot of information. So remember that Venn diagrams show relationships based on the bubbles that they are in. So a figure that's both a rectangle and a rhombus is a square. Venn diagram illustrates this relationship among parallelograms. Venn diagram is a diagram that uses overlapping circles to represent the relationships among sets. So we can see here that in the big circle, so this big circle, we have parallelograms. Everything that's inside of here, including A, C, and D, and of course B is a parallelogram. If it's on the outside, we would consider it not a parallelogram. So E, F, and G are not parallelograms. And then we can go further. If it's in this circle, then we would consider it a rectangle. So both A and C are rectangles. If it's in this second circle, then we would consider it a rhombus. So C and D are rhombuses. And where they overlap here is C, a square, just like we discussed earlier. So we're going to use all this information to answer 10 through 14. So which figure is a parallelogram? So it's in this big box, in the big circle, but not a rectangle or a rhombus. So it can't be in this square, can't be in this circle. So we're looking at a parallelogram that's not a rectangle or a rhombus. So we would be looking at B. Okay. Number 11, which figure is a parallelogram? So once again, we're in this big circle. And a rhombus, so now we're in this one, but it's not a rectangle, so it can't be in this circle. Well, that means that if it's a parallelogram and a rhombus, but not a rectangle, then we're looking at D. Okay, continuing on. Which figure is a parallelogram? So once again, in the big circle. And a rectangle, all right, now we're in this one, but not a rhombus, so we don't want anything in that circle. So we have left A. Okay. Which figure is a parallelogram, a rectangle, and a rhombus? Well, the only place that that works for all of those is right here at C. It has to fit all of those descriptions. Lastly, which figure on a Venn diagram are not parallelograms? So we don't want to be in the circle whatsoever, so we're looking at these out here, and those are E, F, and G. Remembering that because, and this is the explanation because they're not inside of the parallelogram circle, we would consider them not to be parallelograms. And if we looked back at those figures, we would say they don't have two pairs of parallel sides. Okay, now the next part, if we were in class doing this, we would be looking at a video about the golden ratio. If you would like to plug those into YouTube, both of those are great videos about the golden ratio. But the golden ratio is a sequence of numbers that creates a ratio as you continue along the pattern that shows up in nature, in art, in human beings quite a bit. It describes a lot of structure that we see in our world, especially when you look at things like in nature, like shells or flowers, or even this succulent right here. What you can see here is this pattern of a swirl that works with the golden ratio and the Fibonacci sequence in order to describe this pattern that we see a lot. So if you can, plug in that URL to YouTube and watch about it, but in this lesson, it explains it a little bit, and it says one special type of rectangle identified by ancient Greeks and found frequently in art and architecture is the golden rectangle. The ratio of the sides of the golden rectangle, it's not a rational number, meaning it has a decimal number that goes on forever. If the width is 1, then the length is 1 plus 1/2 times the square root of 5 minus 1. Here is an example of the golden rectangle. So you can see this side length of 1, and then a side length, like it said, 1 plus 1/2 times the square root of 5 minus 1. If we draw a segment through the golden rectangle to form a square, so a 1 by 1 is basically what this is, 1 by 1, we also form a smaller golden rectangle. So the ratio of this box is the same as the ratio of this big box that we had earlier. And we can continue doing that. If I were to split this into a square, okay, if I were to take this rectangle and split it into a square and another rectangle, this rectangle would have the same ratio as before, and you can continue dividing it up forever and ever and ever, getting smaller and smaller boxes, but continuing this ratio. What we saw up at the top when we first looked at this ratio was a spiral that consistently goes through this. What happens is we end up working through these boxes. It's kind of hard to draw, but we can make this spiral going through these boxes in a nice swoop over and over and over, continually getting smaller, but continuing that pattern as well. So it says, with a calculator, find the length of the largest golden rectangle shown above to the nearest tenth. So what I would encourage you to do is actually do this without a calculator first to practice with those radicals. And that comes from taking this 1 plus 1/2 times the square root of 5 and then minus 1 and estimating the square root of 5. So remember how we do this. If I had a number line and I were to look at, here's my 0, my 1, my 2, my 3, then I could actually say the square root of 1 is the same as 1. The square root of 4 is the same as 2, and the square root of 9 is the same as 3. Well, if I were to estimate where the square root of 5 falls, it definitely falls between this root 4 and root 9, pretty close to 2. All right, and so maybe I would estimate, maybe I think that the square root of 5 is 2.2. So I would multiply it out. 2.2 times 2.2, we get 4 and 4, 4 and 4, gives us 4.84. Pretty close to 5, but not quite. So we try again. 2.3 times 2.3. We get 9 and 6, 6 and 4. So we get 9 and then 12, 5.29. Well, I've now straddled this 5, getting really close to it. Which one is actually closer? Well, this 2.3 is off by 0.29, and this 2.2 is off by 0.16. So I would actually say that 2.2 is closest to the nearest tenth. So I could now replace the square root of 5 with 2.2. And I could then estimate the ratio with this nearest tenth. So 1 plus 1/2 times 2.2 minus 1. Well, continue simplifying in the parentheses. 1 plus 1/2 times 1.2. Half of 1.2 is 0.6, so 1 plus 0.6 is 1.6. And that is actually the ratio to the nearest tenth. We did figure it out even just by hand. It's a good practice to do. So 16, what are some whole number pairs of side lengths that form rectangles that approximate the golden ratio? Well, one part of the golden ratio is knowing the Fibonacci sequence. The Fibonacci sequence is a sequence where we start out with 0 and 1. To get the next number, I add up the previous two numbers. So 0 plus 1 is 1. And I continue this pattern. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5, then 8, 13, 21, and so on and so on. If I were to look at some whole number pairs of side lengths that form rectangles that approximate it, I would be looking at adjacent numbers here, consecutive numbers in the Fibonacci sequence. So maybe I would say some pairs like 5 and 8, since those are next to each other, or 8 and 13, or 13 and 21, or 21 and 34, and so on and so forth. The higher and higher numbers that we get with the Fibonacci sequence, the better the ratio is. It's a really cool sequence. Check it out if you can, especially with those videos. Okay, continuing on, we're going to look at some symmetry here, answer a few more questions. This is definitely a longer investigation, but that's okay. We look at a lot of really good things. So a student made a model of a rectangle made out of straws and pipe cleaners. Then the student shifted the sides so that the two angles became obtuse and two angles became acute. So same lengths here. This length corresponds to this one and it's the same. This length is the same as this. They haven't changed the length of the straws. They've just shifted them. So what actually happened with figure J and K? Let's see. So is figure K a rectangle? We look up here. Does it have those 90-degree angles? Yes, it does. So figure K is definitely a rectangle. Is figure K a parallelogram? Sorry, I looked at the wrong one. Is figure K a rectangle? This is K. And no, it is not. Is it a parallelogram? And we would say, yes, this is parallel to this. Here and here is parallel, two pairs of parallel sides, so yes, it's a parallelogram. Did the lengths of the sides change when the angles change? And we would say no. Those straws or pipe cleaners are still the same, just the angles changed. Does the perimeter of figure K equal the figure of J? And we would say yes. Because those side lengths didn't change, it still has the same perimeter. We could even make a check of this. We could say this is 2 by 3, so 2 and 3. Well, this one would still be 2 and 3, 2 and 3. So they each have the same side length of, or perimeter of 10. Okay, so as the sides of figure K are shifted and obtuse angles become large and the acute angles smaller, in what way does the area change? I read that before I even read number 20. Sorry about that. Does the area of figure K equal the area of figure J? Well, if I look at this, and if I were to make it really severe, really different, okay, so instead I shifted these really, really severely, so something like this, would we say that has the same area? And we would look at this and say 6 units squared. Does this have an area of 6 units squared? And we would say, no, that does not look the same at all. And it's true that it's not, because remember, to get the area of parallelogram, I take the base, in this case 3, and multiply it by the height, the perpendicular height, which in this case looks like, if I were to estimate, maybe like 1. So it looks like probably the area is much, much smaller than what we had before. So no, the area is not the same. And as we shift those to be even more severe, so bigger obtuse angles, smaller acute angles like we had in the second drawing, what way does the area change? It gets smaller, much, much smaller. Okay, so as we get that more severe, as we squish it down, the area gets smaller. So 22, the four angles of figure J total how many degrees? So figure J right here, we have a rectangle with 90-degree angles, so we would say, okay, all of those together would of course be 360. And how do we know? This is a rectangle, so 90 degrees in each. Sorry about that. Okay, so, all right, we're still all good here. Number 23, what is the sum of the measures of four angles in figure K? So if we look at figure K, even though it doesn't have the same area, that doesn't mean that we don't still have 360 degrees in this quadrilateral. All quadrilaterals still have 360 degrees. So even though we changed it and said we have different angles, it's not actually taking away any degree measure in this figure. How many degrees are in a full turn all the way around is also 360 degrees. Okay, interesting kind of a note there. Number 25, if you trace with your eraser figures J or K, you'll find your eraser heading in a direction opposite to the direction you started after tracing the two angles. This means your eraser has finished half of a turn. How many degrees is half of a turn? So if I were to take this guy up here and I were to just sketch out two sides, here's one and here's two, so I'm heading in this direction. And then if I were to go here and here, I would be heading in this direction. If I just do two of the angles, then I'm heading towards the right. Two other angles, I'm heading towards the left. That's a 180-degree turn. Okay, so in figure K, the measure of an obtuse angle and an acute angle total how many degrees? Well, I have completely opposite directions that I'm going, which means I must have 180 degrees in that obtuse and acute angle together. All right, 27. If an obtuse angle in figure K measures 100, what does the acute angle measure? Well then, if I know that the obtuse and acute together measure 180, and one of them is 100, 180 minus 100 is 80 degrees. So I would say the acute must have been 80 degrees. So similar idea here, we have a parallelogram. If this angle here measures 70 degrees, this acute angle is 70 degrees, well the obtuse angle has to add up to 180, so 180 minus 70 is 110 degrees. So that would be the measure of my obtuse angle. And it's the same as angle B here, so 110 for angle B. So if angle A measures 70 degrees, then D is also 110. And lastly, use the information you found in question 28 and 29. Well, if this is 110, 110, and 70, it has to add up to 360, leaving only 70 degrees left for C, and you can check that out for yourself. All right, lastly, we're looking at some symmetry. A figure has reflective symmetry if I can divide it in half with a line so that each of those halves are mirror images of each other. Think about a mirror and how it reflects back your image. Just like this, if I were to take this line and fold this figure along the line, it would come up and touch exactly this half, and this half would be the same. So we use that and call that blue line that we had a line of symmetry. All right, so let's answer some questions. And feel free to sketch these out, look at all of those. We are looking at A, which was a rectangle, B, which was a parallelogram but not a rhombus, C, which was a square, and D, which was a rhombus. Okay, so 31. Figure A has how many lines of symmetry? So I am going to change colors here so you can see these lines of symmetry. So figure A has how many lines of symmetry? Well, if I were to cut it in half this way, it would definitely be the same, and this way would be the same. So for sure 2. Could I potentially do it this way And we would have to say no, because if I were to kind of reflect it back on itself, it would actually look something like this. We would have this one here, and then we would have this one like that. Okay, take a piece of paper like an 8.5 copy paper, and you'll see what I mean if you were to fold it on a diagonal. Okay, and you would see, no, that doesn't actually work. So that dotted line that I have would not work for this rectangle. We actually only have 2 lines of symmetry. All right, how about this next one? All right, if I were to cut it in half this way, and no, that wouldn't work. If I were to cut it in half this way, no, that wouldn't work. It wouldn't be exactly the same on each side. How about this? And even though it looks kind of similar, it'll have the same issue as our rectangle. And same if I did it this way. Because it's not a perfect rhombus, we actually have 0 lines of symmetry for figure B. How about C? This one could have a lot. And it does. We have 1 down the middle, 1 horizontally, and then this one actually, since it's a perfect square, does work to have corner to corner and another corner to corner. Other than that, we don't have any more lines of symmetry, so we just have 4. And then even though this rhombus does not have a line of symmetry horizontally or vertically, this one actually does work from corner to corner since it's a rhombus, a true rhombus, and from my other corner to corner. So 2 lines of symmetry. All right, 35. Does a line of symmetry for figure A pass through the sides or the angles? And we would say in this case, the sides. Okay, that's the only way that we got it to work. And then for D, so this one up here, does it pass through the sides of their angles? We would say in this case the angles. The sides didn't work to actually cut through this. And 37, does a line of symmetry for figure C pass through the sides or the angles? And we would say in this case through both of those. We had some through the sides and some through the angles. Last type of symmetry is rotational symmetry, and last piece of this investigation. As a figure turns, its original image appears in less than a full turn. For example, as we rotate a square, its original image appears every quarter turn. So if I were to do this, let's say I were to name these sides, side A, B, C, and D. If I were to turn this 90 degrees, and now I have my sides like this, A, B, C, and D, since this is a square, we still have the same image. If I were to rotate it again, have A, B, C, and D, we once again have another image of it. And I could rotate it one more time, A, B, C, and D, in order to see that, yes, this definitely has a lot of rotational symmetry. And we say, since the original image appears 4 times in a full turn, we say that a square has rotational symmetry of order 4. Because when we turn it all of those times, and we could even draw this last one, and it would be back to its original state, A, B, C, D, we would say that it has order 4 for the rotational symmetry. Kind of hard to imagine, but draw these out and see how many times they have rotational symmetry. I'll just do a couple of these. So we're going to go through A through G, but we've already seen C, so we'll skip that one. So figure A, my rectangle. If I were to name these sides, I would say A, B, C, D. And if I were to rotate this 90 degrees, then I would have this rectangle that, even though it is the same rectangle, it doesn't look the same. So it didn't actually work with that turn. How about maybe with another turn? And we would be back to this. And we would say, yeah, that actually worked. We do it one more time and we see up and down like this. And then by the next term, we're back to normal. So we would say, actually, we got 2 turns in this in our full 360 degrees. So we would say, yes, it has order 2. Okay. How about with B? This is our parallelogram that looks kind of like a rhombus, but it doesn't have the same sides all the way along. So we have our figure like this. After one turn, it's going to be, and this is kind of hard to draw here, it's going to look like this. So not the same. By our next turn, we have it, and it's going to be going kind of like this. So once again, it doesn't look the same. With another turn, it's now going to be like this. Another turn is still not going to make it work. And so by the time we get 360 degrees around and see it again, we would say it doesn't actually have rotational, sorry, I didn't draw this correctly. This one actually should have been again like this. Yep. And then, so we do see it once within there and twice by the time we get all the way 360. So similar to the rectangle, we say, yes, it has two. Kind of hard to imagine how to draw those, but we do actually see it twice. Okay, so our parallelogram worked just about as well as the rectangle, but not as well as our square. And then figure D, our rhombus. Okay, so perfect here. And it really works if you take a piece of paper and actually turn it for yourself so you don't have to redraw it every time. Hard for me to do here. But you can imagine, just like our big parallelogram, we do actually see it twice. So this one, not going to be the same. By the time we get here, we do actually have our rhombus again. By our next turn, not going to look the same. And by our final turn, we have that again. So we would say yes with order 2. Okay. And then our next ones, because they're such funky shapes, I have a really hard time believing that they're ever going to have rotational symmetry, because any of those sides, if they're all different, then if I were to turn them, they're never going to look the same when I turn. So for example, if I were to take my kite here, here's my kite, so I'm looking at G, and I were to rotate it once, then I have the small point going this way, so that didn't work. I rotate it again, now my small point is turned down, that didn't work. And another time, now my small point is going that way, didn't work. So that by my last turn, once I do see it again, I say, well, none of these actually worked, none of them. So I would say, no, this does not have rotational symmetry. Turns out that when you do that for figure E and for figure F, none of those have rotational symmetry, because by the time that you get to 360 degrees, you see it again, but you've never seen it the exact same up until that point with all of those 90-degree turns. All right, well, we looked a ton at our quadrilaterals with their symmetry, with how to name them, even with our golden ratio. And I hope this video helps with homework and for studying.